Bao Wang, who will be starting at University of Utah in the fall, will be talking about DP-LSSGD, a stochastic optimization method to lift the utility and privacy preserving empirical risk minimization.
So thank you, Richard, and also thank you the organizers to making this event happen. And I can imagine how difficult it is. So today I'm going to talk about the DP-LSSGD, a stochastic optimization algorithm to lift the utility in privacy preserving empirical risk minimization. So the title is quite long. In particular, this DP-LSSGD, I remember last year, Thomas Schormer said this name is very difficult for people to remember. So I think we should try to figure out some better names. And this is a joint work with my collaborators at UCLA and also my postdoc mentor, Stan Ocean. So I will talk about the ethical issues in machine learning. So today, machine learning achieves tremendous success in many applications like the recommended system, autonomous driving cars, and many others. For those tech companies, they use the machine learning as a service, where behind this, they use a lot of training data, and they gather this training data without inform the users about this. Well, then this usually violates the privacy requirement. And once we train a machine learning model and then we release the model, the adversaries basically can attack this released model to recover some of the training data. For instance, in the membership inference attack, we can determine if some given instance is used to train the image, to train the machine learning model or not. Also, in the model inversion attack, we can even recover the portrait of a person, given the person's name only. For instance, this is a very famous example. Basically, suppose this person's photo has been used to train a face recognition system. And after this face recognition system being released, and then we can attack this by using the model inversion attack, we can essentially recover a very good image of this person. Well, not only membership inference attack and the model inversion attack, but also the data abuse has been in many areas. For instance, in the Netflix recommended computation. Around 15 years ago, Netflix released their anonymized data for the participants to develop a better recommended system. However, people can recover this anonymized information by simply do a correlation with some public domain data. Also, in the genome research, the privacy of this genome data can be easily recovered. And also, we can recover the person's information from this genome data. For instance, typically, the genome sequence contains if a given person has some disease or not. Also, we can, together with some third-party data, we can recover from this genome data to determine a specific person. So then this data privacy issue and more generally the ethical issue has drawn a lot of attention recently. In the industry, there are lots of celebrated protocols for the privacy preserving machine learning. For instance, the federated learning. In federated learning, people do not the machine learning are not happened at the central server. Instead, machine learning is happening at the edge devices. And this data are stored in these edge devices. Every time the machine learning model is updated locally, then this update will be sent to the central server. The central server will aggregate them and send back to the local devices. So this is the federated learning system. Also, mathematic rigorous definition is called the differential privacy. The key idea is I try to randomize this optimized machine learning model. For a given input, the output will be a distribution instead of a point estimation. So then this, if this noise this randomization is high enough, then for a given two adjacent input, you cannot distinguish the output. Then this guarantees the privacy. Also, in older days, the multi-party computing and the k-anonymity, all these things has been used to make machine learning more private. Well, we focus on this mathematically rigorous definition called differential privacy. As we mentioned, the key idea is first, given an algorithm, typically machine learning algorithms like the deep neural network or the classical gradient boosting decision tree, this type of algorithm, all deterministic. A deterministic algorithm cannot guarantee cannot guarantee the privacy. So then the idea is I try to inject noise into this deterministic algorithm to randomize them. And then the randomized algorithm we denote it as A is epsilon delta differentially private. If for any two adjacent database, like adjacent database D and D prime, where they share a lot of the common data. And D has an actual girl in this data set, and the D prime has an actual boy. And then we feed this two data sets into a randomized algorithm. Then we get the output. Because this algorithm is randomized, so the output certainly will be a distribution. And if, for instance, we add this noise to be simple enough for us to analyze, like the Gaussian noise, since Gaussian noise is very simple, it's basically uniform on a sphere, then we can enforce this guarantee. We see that for this any two D and D prime, if the probability of AD in any observable event S and AD prime in this S, they satisfy the probability of AD in S less than or equal to E to epsilon probability of AD prime in S plus delta. Okay. In this case, then we call this this is epsilon delta differentially private. So if this epsilon and delta are small enough, that means essentially these two will be almost overlap with each other. So this is a celebrated definition due to Cynthia DeWalk and some of her postdocs and students. Okay. Then in machine learning, to achieve the differential privacy, typically we can do in the following way. Machine learning problems are formulated as the following finite sum optimization, where n is the number of training data, and on each training data we can compute the empirical risk, okay, and then just do this average. So to randomize this algorithm, because finally what we get is just the machine learning model, the model and also this weights. Okay. So for instance, we can first compute the weights, and finally we can add a perturbation to these weights. However, this philosophy works for the classical convex optimization based machine learning models. But for non-convex machine learning models like deep neural network, if we perturb the output a little bit, the machine learning model, the utility will completely gone. For instance, suppose we train a residual network for ImageNet classification, we can get perhaps 80% of top one accuracy. But if we perturb this a little bit, then the accuracy can drop to 0%. A better algorithm is instead of perturb the output, I perturb the gradient on the fly. Each time when I compute this stochastic gradient, I inject some noise to guarantee this noise, this gradient is private, such that finally I aggregate them, then the result I obtained still is private. Okay. So then this is called differential private SGD. The key challenge now is how to quantify this Gaussian noise to guarantee a given privacy budget. If we only do one step, then this problem will be easy. Because suppose I have two quantities, and these two quantities differ by a certain amount. Then I can first compute the sensitivity, and then add a large amount of noise. So then this, for only one step, this n is easy to compute. But the key challenge is we have many steps, so we need to compute the privacy loss aggregation. Then, like around 5 years ago, a very famous algorithm called a moment account, and later some people make that more rigorous, called Rani differential privacy. They invented this tool to quantify this privacy loss. Then, by using this moments account, we get this privacy budget. So, suppose each Fi is Lipschitz, then this is a rigorous. This is a reasonable assumption. And given the total number of iteration t, and also given the privacy budget, then we only need to inject this amount of noise. This Gaussian noise is characterized by its variance. Now we can guarantee epsilon delta differential privacy. So, but the problem is once the model is private, of course the utility will get harmed. for instance, during the training, if we train a model that's non-private, we do not enforce any privacy, then this converges very rapidly. Well, if we enforce some privacy, like epsilon is 0.02, I think delta is 10 to minus 5. Delta should be scaled like 1 over n. N is the number of training data to guarantee the membership privacy. So then once we enforce this privacy, the convergence gets slower. And if we enforce a stronger privacy, the convergence gets much more slower. And meanwhile, the validation also gets slower. And also the accuracy of the resulting model. In particular, after some regime, like when epsilon is around 1, if we further increase the privacy, the utility will drop very rapidly. Okay. So then this raises the question, can we do better than DP-LSSGD in training machine learning models with legible actual computation and memory cost? We want to improve the utility without hurt the privacy. So then we propose this algorithm called DP-LSSGD with Laplacian smoothing. So basically my postdoc mentor figured out this matrix. And then the nice thing of this matrix is a circular matrix, almost a tridiagonal, and also positive definite because it's diagonal dominant. And since this is circular, then we can use the fast Fourier transform to compute this efficiently. And this matrix, the condition number is small, 1 plus 4 sigma. It's independent of the dimension of the problem. So this is quite nice. Then if we do this in the gradient descent, since the condition number is 1 plus 4 sigma, so it's like very small condition number, it will not hurt the convergence. Almost the same as the gradient descent. Also regarding on the privacy budget, because this matrix is a post processing, so this will not hurt the privacy. We can understand this in the following way. Suppose I have some private information. First, I use noise to encrypt this private information. After this information gets encrypted, then no matter what I do for the post-processing, suppose I do not know how I encrypt this information. After this post-processing, this information is still encrypted without any privacy loss. Okay, so then this is the algorithm we proposed. This algorithm, why we do this? Because this is a deloising operator. Since we can consider this the following diffusion equation, okay, with the Neumann boundary condition and given initial condition. This initial condition is just the signal. For instance, in the one-dimensional case, I have a sine function together with some Gaussian noise. Then after I do this diffusion, basically I can remove the noise and make this better. And then if I have this 2D information, I add some noise, and then I do some diffusion. I get this smooth information. Then actually the Laplacian operator is essentially just I do the backward Euler in time and the central finite difference in space to discretize this system. Because this is backward Euler in time, so this is unconditional stable. So I can use the arbitrary large delta t. So this delta t is exactly the parameter sigma we showed here. So this delta t is a sigma parameter, and this matrix is a deloising matrix. I first add some noise, and then I remove the noise. So this helps the optimization. Moreover, I have the following concentration estimation of the Laplacian operator. Because I add noise, add this Gaussian noise to this quantity, and then I perform this Laplacian smoothing. So then I need to estimate what will happen after I do this. So on this Gaussian noise. Then I have the following concentration estimation. For the Gaussian noise, the L1 norm, the L1 estimate, we have the A sigma x. X is just the random Gaussian noise. L1 norm less than or equal to alpha 1 x1 is bigger than this probability. And this probability is exponentially small. Actually, it's more than exponentially small because this is like e2 minus n squared. So this is very small. And also for the L2 norm, this is also very small. So then we can leverage this tool to analyze the utility guarantees. This concentration actually can be understood very easily because for the Laplacian operator, the inverse, A sigma inverse, all the eigenvalues are less than 1, except one of them is exactly equals 1. So then if we draw out a small cone around this angle, the eigenvector around the eigenvalue, so then all this all this will converge to 0. So then we get this concentration estimation. And then
you just have a minute left.
Okay, then we can estimate this utility basically based on this. We can use some simple harmonic analysis tools to analyze the exact bound of this utility. Okay. Then we perform an experiment. So for this experiment, we see that we do this logistic regression on the MDC classification. We show that when we have this Laplacian smoothing, we can significantly speed up training and improve the generalization accuracy. In particular, when in the high privacy regime, like epsilon is 0.1, so then we can increase the accuracy by 3% for free. So then this is the paper just got accepted to the conference, MSML, and the code is available on my GitHub. And we have lots of recent progress along this direction. For instance, we can do the federated learning. And also we have noticed there is a fundamental trade-off between the utility and the privacy. Moreover, with one of my friends at the Wharton Business School Statistics Department, we have also tried to analyze some better privacy preserving machine learning mechanisms. Because for the gradient perturbation, this still hurts the utility a lot, because we have some result on the fundamental trade-off between utility and privacy for the gradient-based perturbation. Okay. So that's all about my talk. Thank you.
Thank you very much. We have a question here that I'll save for the Q&A because I want to ask a question myself right now. I'm just for my understanding. So the DP component is to stochastic gradient descent is just adding some amount of noise?
Yes, yes. The key challenge is how much noise to add, then to quantify the privacy.
And then the Laplacian smoothing is sort of a separate transformation that could be considered independent of the DP component. But you put them together, and together the random noise and the Laplacian smoothing, is this, well, I guess this is the same question now to the person. Is this equivalent to adding some sort of correlated noise?
Well, this is not correlated. The reason is, first, this matrix is independent of noise. I do not have any prior knowledge of this noise. So then this will not make the noise correlated. Yeah, that's a very good question.
Got it. Yeah. Okay, maybe we can discuss more in the Q&A. Thank you again,
Thank you
Bao, for your talk.
Thank you.